So now let's go on to problem 835. 835, we now deal with moments of inertia, which play an equally important role in rotation, and you'll see the connection between the two. I have to define an axis of rotation, and the moment of inertia about that axis of rotation is defined this way. This is a scalar, it's not a vector, and it requires a little bit of an explanation. Suppose I have here a rod, and right through the center I would have an axis which I call A1. Now the way that we defined Ri is as follows. Ri is measured from little mass elements Mi perpendicular to the axis. That's the definition of this Ri. So in this particular case, if I slice out here a little mass m of I, then I would have a position vector measured from this point, because that is the perpendicular from Mi to the axis. So this would be Ri. And if I sum this over all values of Mi and all values of Ri, then I will get the moment of inertia. There's never any danger of being it negative, because Ri is being squared. And if this were a rod with uniform length L and the mass distributed uniformly, then I1 indicates this axis, equals 1/12 mL squared, and you can look that up in almost every table. If you had a solid sphere, so this is solid, and it is a sphere, and if the mass is uniformly distributed, and if I take an axis of rotation right through the center, and if it has a radius r, and if it has a mass m, then let's call this axis A1, then I of 1 equals 2/5 m r squared. You don't want to remember these things, you can look these up in tables, and you have some of the tables in your book. Now there are two very, very, very key theorems that will help you to solve almost all moments of inertia using the values that you see in the table and manipulating them a little bit. And one is called the parallel axis theorem. If I have an axis A1 through the center of mass, and I have an axis A2 which is parallel to A1, but it is at a distance d, then I2, moment of inertia relative to this axis, equals I through the center of mass, which in this case is axis 1, plus md squared. Comes in extremely handy, and today you're going to need it. So if we take the case of the rod, the uniform rod, and we know what the moment of inertia I1 is to the center of mass, that was the 1/12 mL squared, and if there is a rotation about another axis, A2 parallel to A1, so the whole rod rotates about this axis, then I2 equals I1 plus md squared, if m is the mass of the rod, and this is d. And this will come in very handy, and of course you can do the same with the spheres if you know the moment of inertia relative to this line. If you now have another axis with a distance d, then you can apply exactly the same equation. And then there is another theorem, which is called the perpendicular axis theorem. Perpendicular axis theorem. And this only works when you work with very thin sheets. So suppose you have a very thin circular disc, very thin, and I have an axis of rotation perpendicular to the paper. Let's call that the z direction. So Iz, about this axis, and you may try to prove that, it's not so obvious, I call this the x-axis and this the y-axis, is also equal to ix plus iy. So rotation about this axis of the plate or rotation about this axis of the plate. And you can also do that for this point here. So also the moment of inertia rotation about this axis would be the same as the moment of inertia about this axis plus this axis, as long as they are perpendicular to each other. Well, if we are very specific, the moment of inertia of a disk, of a thin disk with uniform mass, and it has radius r, and it has mass m, that is 1/2 mr squared. This can be looked up in your tables. And so it follows immediately that Ix equals 1/4 mr squared. Because Ix and Iy must be the same for reasons of symmetry. They both go through this point. There's no reason why one would be larger than the other. So this is 1/4 mr squared. And so if I pick any other axis to the center, I call this A2, then it's immediately that this is also I2. Now once you know I2, you could easily find the moment of inertia of rotation about this axis if the separation here is d. Because that now, let's give this axis a number, let's call it A3. So now the moment of inertia I3 equals the moment of inertia going through the center of mass along the line A2. So that is I2 plus md squared. So you see here that I have used both the parallel axis theorem and I have used the perpendicular axis theorem. And sometimes you have to manipulate these things a little bit and massage them a little bit because you're stuck to the numbers, to the specific cases given in your tables. The tables in general are quite complete. You have disks, you have spheres, you have plates, cylinders, rods, you name it. But in any case, if your favorite one is not in there, you have to somehow manipulate it and massage it a little bit. And that's what this problem is all about. You have a square plate. For now, I will call this B2 and B1, although very shortly I'll make them the same because they are the same. It is a thin plate. And you are being asked to calculate the moment of inertia of rotation about this axis. And let us call this axis A5. And this is at an angle of 45 degrees. Well, what I found in the study guides, that for rotation about this axis, so the whole thing rotates about this axis, the flat plate, that result, I1 equals 1/3 m times B2 squared. So that's a given from your table. Well, I will now forget the fact that B1 and B2 are different because they are not. So we'll write down for this B and we'll write down for this B. And so that is 1/3 m times B squared. But now I have to somehow find this one. Well, I'm first going to use the parallel axis theorem. And I'm going to move this one to a parallel line right through the center of mass. And let's call this one A2. Well, then it should be immediately obvious that I2 plus M1 plus M is the mass of this plate, times 1/2 B squared must be I1. This is the parallel axis theorem. Because the separation D equals 1/2 B. So here you see your D squared. So now we know what the moment of inertia is about, rotation about this axis when it rotates like this. Well, I also know that if I take this axis perpendicular to the paper and I call that A3, then I know that I2 must be 1/2 I3. for the simple reason that this moment of inertia is the same as the sum as this one plus this one. And so it's immediately obvious that it is 1/2 I3. Now I'm going to, let me take a different color. Now I'm going to take an axis which goes through the center, but which is exactly parallel to this one, and I call this A4. And I want you to appreciate, even though that may not be so intuitive, that this I2 must also be the same as I4. The reason being that the moment of inertia about this axis, the vertical axis, must be the same as the moment of inertia about this axis plus the moment of inertia about this axis which is perpendicular to it. And you can call this x, and you can call this y. And so this one and this one obviously are the same because of symmetry. And so it's immediately obvious that this one, as well as this one, must be half of the moment of inertia about this axis, and so you see that I4 becomes I2. Well, now you're well on your way. Once you know what the moment of inertia is about A4, you would have no problems in going from 4 to 5, which is our final goal. You use again the parallel axis theorem, and you are on your way. So you've seen an example here whereby you have to manipulate things a little bit. It's almost like a puzzle, a crossword puzzle. I like it actually. It's kind of cute.